Today, we're going to continue working on finding derivatives. Once again, we're trying to avoid having to use the definition of the derivative because it is so algebraically cumbersome, and we might not remember all that algebra. So we're going to learn some new processes that'll be a shortcut to using the definition of the derivative. And yesterday, we learned the big one. This is not officially known as the big one. This is just what I call the big one. The derivative of x to the n is nx to the n minus 1. This covers a lot of ground. We saw this work on polynomials, we saw it work on negative exponents, and we saw it work on radicals. So we've got our algebraic stuff mostly covered with this one simple rule. And there's two steps. We multiply by the exponents and subtract 1 from the exponents. What we want to notice for this particular rule is that this is a rule for powers of x. That is, the base is the variable. So the x, we're taking the derivative with respect to x, and x is the base. The exponent is constant. The base is variable. The exponent is constant. So we're looking at constant powers of x. This rule plus algebra gets us we get a lot of mileage out of this rule plus some algebra. So if we can write a function as power terms with powers of x, then we should, because then we get to use this rule. So if we can write powers of x, then we should write powers of x. If we can write powers of x, then we should. If we can write powers of x easily. So for example, yesterday we looked at an example where we had a binomial squared, and we just multiplied it out and took derivatives a term at a time. We want to get a term at a time for our derivatives, because then we get to use this rule, and life is pretty simple. So the distributive property is our friend. So for example, yesterday, if we started multiplying things out, we just started using algebra to our advantage. So if I wanted the derivative of 2x minus 3 squared, I can multiply out the 2x minus 3 and get powers of x. Right now, I don't have powers of x. I've got a power of a binomial. I want to write a bunch of x to the n. So I'll just multiply this out. This will be the derivative of 2x minus 3 squared, which will be 4x squared minus 12x plus 9. Then we get to use our rule. The derivative of 4x squared is 8x. The derivative of 12x to the 1 is minus 12x to the 0. The derivative of 9x to the 0 is 0x to the negative 1, so we don't write anything. So here, it's easy to write powers of x. It's easy, we can just distribute to write terms with powers of x. We do have to remember that we can apply the distributive property in other scenarios. So for example, if I want to take the derivative of, let's say, x squared plus 3x plus 4 divided by x squared. Right now, we don't have powers of x, but we can use the distributive property to write terms with powers of x. So I can distribute the x squared and write this as the derivative of x squared over x squared plus 3x over x squared plus 4 over x squared. Here we are, we're using the distributive property to write terms with powers of x. We want to use this super simple rule. I want to do nx to the n minus 1, so I'm going to try to make things, rewrite the expression to make that happen. So in this case, we're taking the derivative. X squared over x squared is just 1. 3x divided by x squared is plus 3 over x, or 3x to the negative 1, because we're trying to write powers of x. And then 4 over x squared is plus 4 x to the negative 2. Now we can use our favorite rule, nx to the n minus 1. The derivative of a constant is 0, because we're imagining that 1 looks like 1x to the 0 power. So if I multiply by the exponents, I get 0 times x to the 0 minus 1. So I end up with 0 for that, from that 1. But the derivative of 3x to the negative 1 is negative 3x to the negative 2. And the derivative of 4x to the negative 2 is negative 8x to the negative 3. So the derivative of a constant is 0. We can imagine it like 1x to the 0 power. So when we multiply by the exponent, we end up with 0. So in both these cases, we just use the distributive property so that we can write terms with powers of x. That means we get to use nx to the n minus 1. And so that makes us happy. Now, there are some cases where we can distribute, but we're not going to want to. It shouldn't be the only tool that we have in the toolbox. For example, if I wanted the derivative of 2x minus 3 to the 10th power, we are not going to want to multiply this out. We're going to want to find a better solution than distributing, because I don't want to multiply 2x minus 3 to the 10th power. We could, but we don't want to. And there are some times that the distribution won't help us. So if we have more than one term in the denominator, so for example, or if we just have the reciprocal, we can't just rewrite this function with terms that are powers of x. It's a common denominator that we use to add, not a common numerator. So addition is for a common denominator, not a common numerator. I can't write this as x squared over x squared plus x squared over 3x. That's not how numbers behave. So the reason that we can't just distribute is that it's a common denominator, not a common numerator. Common denominator, not numerator. Sometimes students try to invent new algebra rules through will alone. But the rules of algebra are not in place because of some kind of magical thing. The rules of algebra are the way they are because that's how numbers work. And so there's not, I can't distribute the numerator to the terms in the denominator. That's not how numbers behave. Up here, 1/5 plus 2/5 plus 3/5 is 6/5. That's how numbers behave. Common denominator, and we're just undoing that. But I can't just write 5/6 as 5 over 1 plus 2 plus 3. That's not how numbers behave. Any questions? So just for clarification, up here, we're saying something like 1/5 plus 2/5 plus 3/5 is 6/5. But I can't write this where the 5, or we'll just switch those roles and write 5 over 1 plus 2 plus 3 is not 5 over 1 plus 5 over 2 plus 5 over 3. So that's what I mean by it's common denominator, not common numerator. So this particular rule is super useful combined with our awesome algebra skills. If we can write things as powers of x, then we should do that because then we get to say nx to the n minus 1. If it really came down to it, if I said 25% of your final is finding the derivative of this function and all you have is multiplying it out, then you just get to multiplying. Hopefully efficiently, like using Pascal's triangle or something like that. But you just get to multiplying if you can't think of something else. But if it's just like 1 point on a homework assignment, then you're like, oh, you know what? I'm going to wait for something better to come along. So this nx to the n minus 1 business is specifically for when the base is a variable and the exponent is constant. Now what we want to do is just switch those around. I want the base to be constant and the exponent to be a variable. So we want to talk about derivatives of exponential functions. So for an exponential function, the derivative of a to the x. So here a is the base. The base is constant. The exponent is variable. The derivative of a to the x is a to the x times the natural log of a. The derivative of a to the x is the natural log of a times a to the x. So in this case, the base is constant. So in an exponential, the base is constant. The exponent is variable. That's what makes this an exponential function. The base is constant, the exponent is variable. So we use a different rule. The previous rule, nx to the n minus 1, is for when the base is variable and the exponent is constant. The most important version of this is when the base is the base of the natural log. So if we have the derivative of e to the x, we just get e to the x. That's because the natural log of e is equal to 1. So an important version of this is that the derivative of e to the x is e to the x. Recall that the natural log of e is equal to 1. So here's our second rule for derivatives. The derivative of a to the x is the natural log of a. That's just a constant. The derivative of a to the x is natural log of a times a to the x. So for example, if I want to find the derivative of 4 to the x, it's just the natural log of 4 times 4 to the x. The other rules for derivatives also apply. So if I have a constant multiple of 4 to the x, so for example, if I want to find the derivative of 5 times 4 to the x, this is just a constant multiple of my previous one. 5 is a constant multiple of the 4 to the x. Constant multiples just get carried along. The derivative is a linear transformation. It respects scalar multiplication. So this is just going to be 5. Constant multiples just carry along. 5 times the derivative of 4 to the x, which is the natural log of 4, times 4 to the x. The derivative of a constant times a function is that constant times the derivative of the function. The derivative of a constant times a function is that constant times the derivative of the function. The derivative of a constant term is equal to 0. So if my function is, say, 5 times 4 to the x plus 7, this 7 is a constant term. The derivative of a constant term is equal to 0. the derivative of a constant term is equal to 0. So the derivative of 5 times 4 to the x is 5 times the natural log of 4 times 4 to the x, and the derivative of 7 is equal to 0. One thing you should note is that I did not justify this rule. I just said, this is how it works. And most of you are just going to take my word for it. You shouldn't just believe me because I'm in charge. But there is a detailed explanation in the book that you should read before you ask me for my explanation. Mostly because the end result is that we remember that the derivative of a to the x is the natural log of a times a to the x. That's the key thing that we need moving forward. The rest of it is justifying it in our mind. And rather than just grabbing my justification for things, you go out and read about it, and then I can support you in that effort. So I can explain the little bits that don't make sense, if you feel that you need the explanation. Note that to remember this rule, you don't need the explanation. The reason that I'm foregoing the explanation is that it doesn't really add a lot to this particular discussion. It's not interesting enough yet. We just want to get the rule. That makes sense? I'm not deliberately trying to avoid it. It just doesn't add anything right now. We have a different goal, and that's remember this: the derivative of a to the x is natural log of a times a to the x. Any questions?
Yes, Professor Rich, could you please explain the first example again? Derivative 4 to the power of x.
The derivative of
Yes.
this is an exponential function. So this is just using the rule that we had up here, where a is equal to 4. The derivative of a to the x is the natural log of a times a to the x. So the derivative of 4 to the x is the natural log of 4 times 4 to the x.
In other words, a to the x is the same as 4 to the x, isn't it? Correct?
Yeah, a is equal to 4. This
And
example
then,
this the exponential function where a is equal to 4.
got it. And then ln a is mean ln 4. Got it. Thanks. Thanks. Got it.
The key thing that we want to notice is that this is a rule for when the base is variable, the base is constant and the exponent is variable. And we have a different rule for when the base is variable and the exponent is constant. So part of our job is knowing the difference between the two. So for example, if I want the derivative of, let's say, some mixed function, say x to the 5th plus 5 to the x. So here in the first term, the base is variable, the exponent is constant. The derivative of x to the 5th is 5x to the 4th. But in the second term, 5 to the x, the base is constant, the exponent is variable. So the derivative of 5 to the x is the natural log of 5 times 5 to the x. there is something interesting that we can read into this rule for exponential functions. Notice that when we have an exponential function, the derivative of an exponential function is just a constant times that exponential function. So what this means is that the rate of change of an exponential function, so let me write the rule again. So the derivative of a to the x is the natural log of a times a to the x. The natural log of a is just a constant. So one way we can look at this piece of information, we have the function, and here's the function copied over here. The derivative is just a constant times the function we started with. So for an exponential function, the rate of change of an exponential function is proportional to the size of the function. The rate of change of an exponential function is proportional to the value of the function. That is, for larger values of the function, the rate of change will be higher. Moreover, if the function is twice as big, it will be growing twice as fast. This is something that we can observe. We can see populations that will grow exponentially. This is before competition for resources becomes an issue. But if we just set some bacteria to grow in a nice, nutritious environment where they don't have to compete with each other, the population will grow exponentially. So it makes sense that a larger population will grow faster than a smaller population. And if the population is growing exponentially, when the population doubles in size, it will be growing twice as fast. Because there's more members of the population to continue making more members. So that's an interesting thing that we can observe about exponential functions. From a mechanical standpoint, you need to know the difference between variable raised to constant, the derivative rules for variable raised to constant, and constant raised to variable. So we've got two rules that we have to remember now. Don't worry, there will be plenty more than just two. Any questions?
Yes, Professor Lich. On the example, you have x to the fifth power plus 5 to the x power. And then to the right, how come you don't put the ln in front of the 5x to the 4th power?
That's a different function. That is, in that part, that term, we're using this rule. The derivative of x to the n is nx to the n minus 1. So the derivative of x to the fifth is 5x to the 4th. So when it's a variable raised to a constant, this is the rule that we use. But when it's an exponential term, the derivative of constant raised to exponent is natural log of constant times constant raised to exponent.
Yes,
so I use different rules because each term has a different form.
Yes, I see it now. Thanks, Professor. Got it. Thank you.
Any other questions? we need to introduce some more terms. Notice that some more rules for derivatives. So let's take a look at some more derivatives. Right now, we can only find derivatives of functions where we can go a term at a time. The derivative of a sum is a sum of the derivatives. But when we have a product, if one of the factors is not constant, then we need something more complicated called the product rule. Here we have the derivative of a product. So this is for the derivative of a function of x times another function of x. So this is for taking the derivative of a product, a function of x times another function of x. So the derivative of a product is not just the product of the derivatives. Once again, we're not setting this rule up just to make things complicated and make your lives difficult. This isn't about you. Get over yourselves. This is just how functions work. When we came up with the product rule, we had to figure out how all the derivatives interacted with each other. Like I was there. We had to figure out how the derivatives interacted with each other. And the product rule is something that we discovered, not something that we invented. So this is how differentiation works with a product. There's no trick to it. It's just a simple trick. The good news is it's a formula. The bad news is it's a formula. So the derivative of a product, f of x times g of x, is going to be f prime times g plus f times g prime. So the f and g version of it is to say f prime g plus f g prime. The derivative of a product is the derivative of the first times the second plus the first times the derivative of the second. So that's what it would look like in words, which kind of sounds awful. But the derivative of the first times the second plus the first times the derivative of the second. These are the words that I use to remember the product rule. The derivative of the first times the second plus the first times the derivative of the second. We also might say f prime g plus f g prime if you're looking for something a little more efficient. F prime g plus f g prime. Some people remember it in kind of a weird, what I think is a weird way. You might remember it as the derivative of the first times the second plus the derivative of the second times the first. Multiplication is commutative, so you can do that if you want. So you could say f prime g plus G prime F. I don't really care which version you need to use to remember. You do have to pick one. So you're either going to be in camp F prime G plus F G prime, or you're going to be F prime G plus G prime F. And this is called the product rule. It's for the derivative of a product where we have two functions of X. Let's do an example. Let's suppose that we want to take the derivative of x to the fifth times 5 to the x. Before we did x to the fifth plus 5 to the x, we just go a term at a time and life was simple. But now we're going to have to figure out these parts. One of these is going to be the first, the other one is going to be the second. Multiplication is commutative, so we can pick whichever one we want, but I'm just going to go with first things first. I'm going to say f is x to the fifth, so f prime is 5x to the fourth. And then I'll say that g is 5 to the x, so g prime is natural log of 5 times 5 to the x. So the derivative of x to the fifth times 5 to the x is going to be f prime times g, so 5x to the fourth times 5 to the x plus f times g prime, x to the fifth times the natural log of 5 times 5 to the x. Right now, we don't really have a reason to want to simplify this expression, so we'll just leave it as is. I kind of prefer that you just leave this as it is. Mostly because there's not one unified way to rewrite this expression. And if you start rewriting your expressions, you risk writing them incorrectly. Any questions? Plus, once you start rewriting expressions of this form, you all start doing weird different things. Although it becomes interesting to find out who's using the TI-89 to do their math, and who's using Wolfram Alpha to do their math, and who's using some other program. But all the Wolfram Alpha people will write the same weird factorization of this. And all the TI-89 people will be writing the same weird factorization of this. So you should know that if you're just going to use Wolfram Alpha to do your homework, it is super obvious when you're doing that. I couldn't tell, like if you did Wolfram Alpha to do x to the fifth and come up with 5x to the fourth, that wouldn't show. But if you use Wolfram Alpha on this, it's super obvious that you used Wolfram Alpha. Because the Wolfram Alpha tends to factor things kind of weird. It'll give you alternate versions of the derivative and you won't know which one to pick. So you'll pick the fanciest looking one. You know what I mean? I think the best course of action is just to assume that I know when you're lying to me. The reason for this is that I will always know when you're lying to me. But I will not always call you out on your lies. Doesn't mean I don't care. Just that I know. You know what I mean? So this is called the product rule. The derivative of a product is not the product of the derivatives. We have to use the product rule. And for that, we just remember that the derivative of a product is the derivative of the first times the second plus the first times the derivative of the second. Or in terms of f and g, f prime g plus f g prime. Or if you want the alternate, like the primes to go first, f prime g plus g prime f. However you're going to remember it, it's best if there's some kind of rhythm to it. So rhythm always helps you remember things. F prime g plus f g prime. Just takes one measure. Any questions? Comments? Slide remark? This only seems like it's a lot to remember because it's a lot to remember. And it's only going to seem like even more to remember because there's even more to remember beyond all this. We haven't talked about trigonometric functions, and we haven't talked about composition of functions. There's a lot of stuff that we haven't talked about. We've just started. But we've got 3 rules right now. The derivative of a power of x, the derivative of an exponential function, and the product rule. Any questions? All right. Those are going to be our 3 rules for this week. So I'm going to make a homework assignment for exponential functions and then a homework assignment for the product rule. And then we'll talk about the quotient rule and the chain rule starting tomorrow, but they'll be official topics for the following week. All you have to do to get good at this is thousands of problems. You'll know you're being challenged by the work when you start to wonder, when am I ever going to do this? As soon as that question comes up, that's your mind's way of telling you that you don't enjoy this and you would rather go do something else. And so you start searching for some justification to not do your work. And the go-to is, this information is useless to me in my future, which may be true. I would be surprised if in your future career as fill in the blank, you actually had to use derivative rules to find a derivative using the product rule or quotient rule or chain rule or the stuff that we did in this class. That would be really weird. I have a standing offer of $20 to anybody who is in a non-teaching profession who for their job had to find the derivative of some function using the product rule, quotient rule, or chain rule. You could tell how long that rule has been in effect because it's $20, which is just not a lot of money right now. You know what I mean? This is a rule from like the early 90s, late 90s. But remember, stuff that you're going to do in your job is not the point. Understanding calculus is the point. Does that make sense? It's a very ivory tower academic way to look at things. But that should not be surprising coming from an ivory tower academic. You know what I mean? I guess the other point is, don't be so eager to sell your life to some job, because it's just some company that wants to make lots of money. And they'll do what they need to do to get work out of you, like convince you that you're important to the operation of the company. Does that make sense? Don't be so eager to get out there and contribute to this toxic society that we've built, where everybody has to work or they can just die. Spence, you got an opportunity right now to like learn some stuff. So take advantage as much as you can. You know what I mean?
Yes, I do exactly what you mean, Professor Rich.
So anyway, you got to learn your derivative of x to the n. You got to learn your derivative of a to the x. You got to make sure that you know the difference between the two and when to use them. You got to know your algebra enough so that you can use x to the n as much as possible. And you got to start working on the product rule. That's going to do it for today. I'll see you all on tomorrow. Everybody have a good day. And thanks for playing.